Yeah, so welcome to this class. This is a class about a concept we call FHRP, which is Fast Hop Redundancy Protocol. Fast Hop Redundancy Protocol. And so FHRP is a group of protocols. It's a group of protocols which help to provide redundancy at the level of the default gateway. What do I mean? Now, what I mean is that uh, looking at this diagram here, we can see that we have LAN 1 and LAN 2. This is our LAN 1, this is LAN 2. Each and every the PCA in LAN 1, it has their own default gateway, which is 192.168.1.1. And this 192.168.1.1, it actually the IP address of R1. You can see here, it is the IP address of R1. And the other one, the other one is let's look at, so which means the default gateway for PCA is R1 here. So if R1 wants to visit the web server here, it has to send information to R1. The information cannot go through S3 to R3 because PCA only knows R1 and not R3 as its default gateway. When you go to PCB and you check the IP, the default gateway, we see that the default gateway of PCB is 192.168.1.3, and checking from the table, 1.3 is router R3. Okay, so PCB only knows R3 as its default gateway, as it's only way out of the network to the internet. PCA also knows only R1, of course, going to R2 to the internet. That means if we ever remove the link between S1 and R1, PCA will be in problems because PCA will not be able to access the internet. And so is PCB if we remove the link between S3 and R3. So these two pieces, they are very dependent on their specific routers. And interfering with their link to that router totally cuts them off from accessing the internet. And that is now where our question is. So our question is, how can we ensure that in a network, whatever a PC's default gateway goes down, we can have another router that takes over and the users within the network do not experience any disconnection from the network? That is a very, very valid question. Now, as we checked on our PC today, every PC, it only has one place to input the default gateway. Every PC, they only have one space for putting default gateway. You cannot configure two default gateways at a time. And that's why we have these groups of protocols called Hsrp. I mean, that help in providing a default gateway redundancy, so that wherever one default value goes down, the other one can still pick up, and there's a continuation in network access. And that is what today we want to learn about this group of protocols. And we are going to learn, this is just the group name. We are going to learn the specific FHRP protocols, and we'll pick at least one of them. We'll pick one of them and we study it in details. We study it in details. And so for the first hop redundancy protocols, we're going to explain the purpose and the operations of these protocols, what they do, and how is it that they're able to provide redundancy at the level of the default gateway. And so we'll pick one of them, which is called Hsrp, the hot standby router protocols. This is one of the protocols under FHRP. So talking about FHRP, we, like I've mentioned, most end devices are always configured only with a single default gateway IP address. That is common, every end device. Such that if that default gateway ever fails, if that router fails, then the host devices connected to that LAN will lose connectivity to the outside network, okay? And so even if you had a layer 3 switch, it still has, the problem persists. And so this group of routers or protocols called the first hop redundancy protocols, they are mechanisms that provide an alternative default gateway in a switch network where two or more routers that are connected within the same network or within the same VLAN or within the same VLAN. Now, so what Hsrp basically does is that it helps to eliminate what we call a single point of failure. A single point of failure is whereby within your network, you only have one hop in one device to provide a certain functionality. For example, if that router is the default gateway, if that router ever goes down, then the whole network fails. That is what's called a single point of failure. And every network should never have a single point of failure. And that's why we implement what is called redundancy. Redundancy is where you have multiple points of failure so that when one point fails, we still have another one that takes over to provide continuous network accessibility. And so in Hsrp, we implement something called a virtual router technology, okay? Such that multiple routers are going to be configured to work together to present the illusion of just one single router hosts, okay? We have several routers working together. They share a certain IP address and a certain MAC address, and we call it a virtual router, so that when at every one point, only one of the routers can be used to access the internet. But if that router goes down, then the neighboring router takes over to continue with the process of packet forwarding within the network. Okay. And so the IP address that all of them are sharing, we call it a virtual IP, a virtual IP address. And the MAC address, we call it a virtual MAC address. Now, because I would like to paint a better picture of what that does, I want to tell you a story. Yeah, I want to tell you a story here just to be able to understand. This is one of my other parable here to just make us to understand better whatever it is. So imagine this is not a very good story, but it is a very applicable story. Imagine of an individual, human being, or let's say a man. Imagine of a man, and the man is his job is robbery. Eh? The man is a robber. So the man is a robber, and he has his friend. He has his friend. And the major function of the friend is the days when this man is very tired or is very sick. Okay. Then the friend is going to take over and to do the job, you know. So at any one point, only one person goes to work to do robbery. But now, this kind of robbery is a very special type of robbery in that these robbers, they have an agreement or some kind of, you know, friendship, not a very good one, that someone should be proud to have. They have families from where they go to steal, and every family that is their client, and they have some honor when they are going to do robbery to any of the families. And so I'm going to pick an example of one of the families and look at how the scenario looks like. And so imagine the when the thief, the main thief, is supposed to go and steal tonight. Okay. So before he leaves, he makes a call well in advance. He says, uh, good evening. Uh, I'm your usual friend, and I hope by now you know my number, the number through which I'm calling or with which I'm calling. And I'm going to make a visit to you guys tonight at 10 p.m. in the night. And please just make sure that there's no interference. We will come with a lot of respect, you know. And when we arrive, we will show our ID, I mean, hanged on our necks. So we'll show you our ID. When we arrive, we'll also let you know by calling through the same number. And so when we arrive, please make sure that everything is quiet. If you have a dog, just make sure that the dog is kept out of our sight and it's not barking. And if there are any valuable items that you would like us to, you know, to uh, make away with, kindly just put them somewhere open. We do not want to wake you uh, if you are asleep. So we'll get there, show our IDs, uh, pick whatever it is that used to belong to you, but now seems to belong to us, and we live in peace. Those are thieves with honor. You know, they say we are doing robbery without violence, no violence that we're doing. We transfer the position very securely, and please do not make a mistake of calling the police because you're gonna trigger us. And so a few things I need you to note about this thief uh, is that this thief, the mobile number that he uses to call is not his own mobile number. Okay. This thief, he took a mobile number of a person who does not exist, a person who is dead. Okay. So someone died and they left their phone number. So they took the phone number with his SIM card that was registered under the ID of the dead person or the deceased. And then they also took the identification card of this dead person. Okay. And they went and someone designed for them a face mask which looks exactly like the person who is non-living. And so the day the thief makes a visit, he goes there and puts on the mask, which looks exactly like, the non-living, the person who passed on. And he makes a call the person's phone number. That means police cannot track that number. If they track the ID, they'll find this is someone who died long ago. And of course, the face, the ID, the face, the phone number, and the last one is the ID. The identification card used by this thief also does not belong to him. Okay. So just one more time. So he comes, makes a call well early in advance that I'm your usual friend. I'm gonna come pick up, what I need to pick up very smoothly with a lot of peace, with a lot of diligence, and then just leave without any interference. So he gets there 10 o'clock in the night, shows the ID which doesn't belong to him, obviously. Made a call with the phone number, which obviously doesn't belong to him, and shows the ID which doesn't belong to him, and his face isn't one of his own. So he picks stuff and goes away. In another week or so, this guy got tired, or I mean, he got sick, and the friend he tells him that, you know what, you it's your time to go to work today. And so, as usual, the friend makes the call earlier in advance. The friend puts on the same face mask, which belongs to neither of them, and the friend takes the ID card, which belongs to neither of them, belongs to the person who passed on, and picks the same phone number, which belongs to neither of them, and takes the face mask, of course. And he gets there and knocks and picks up what he needs to pick, of course, showing his ID and making the previous call with the same phone number. And so what I need you to note here is that the family do not realize the change from one person to the other here. Okay, the family don't realize that the person who came last week is the person who is coming this week, because these guys have the same calling the same number, having the same face mask, and showing the same ID. And the families here, the family doesn't realize the changeover from one person to the other. And this is a very important scenario when talking about Hsrp. Okay, why? Because, like, looking at this diagram right here, if you can see it, we'll simulate, I mean, we'll think of the pieces down here. This is the family. This is the family. And we do have the main thief is here. Okay. And we do have the friend here. All right. So the family here, I mean, the pieces down here is like the family. The first router, which is the active router, this is like, let me just use another, I want to use another diagram, exactly this one. Yeah, exactly. So the family is down here, as the PC is down here. The main thief is here, this router, okay? And the thief, who is the friend, always on standby, is here in R2, okay? And so we have the dead person here. You can see this router here is put in such a way that it is actually faded compared to all the other routers available here. It's faded, and we are calling it a virtual router. We call it a virtual router. And this virtual router has an IP address, which we will call the virtual IP address of 172.16.10.1. And it does have a virtual MAC address down here as well. And so, of course, R1 also has its own IP at 10.2, and R2 is 10.3. Okay. Now, these three IPs, 10.2 for R1, 10.1 for the virtual router, and 10.3 for the standby router. Now, I want you to understand one thing, that the virtual router doesn't exist. And this is a concept that I take long to explain to my students. And the fact that it's drawn here, it doesn't mean that it's here. You can actually see that it is not connected to any of the devices. And so what happens is that we configure R1, who is the active router, the active thief, with the same virtual IP address and the same virtual MAC address. But we know that at any one point, these PCs down here, they can only utilize the services of one router to connect to the internet up here. Okay. And so R1 and R2 have their own unique IP addresses, but we configure them with a virtual IP address of an imaginary device. We pick an IP address on the same network, and I'm going to show you how to configure that. So we assign the same IP to R1 and R2, but currently only R1, which is our active router, is being used as the default gateway for with these PCs down here. And so the PCs keep on sending information through the R1 to the internet. Now, the day R1 goes down for any particular reason, R1 and R2, the main thief and the thief on standby, are always in communication. So that the day the main thief R1 goes down or is sick, okay, it informs R2 that, you know what, I'm down, please take over and continue providing the services. I mean, to our family, you know, the robbing services to our family. Uh, Very funny indeed. And so R1 and R2 are in constant communication, exchanging messages every few seconds. Okay. The day R1 goes down, R2 picks up. But remember, R2 is using the same virtual IP. So what at the end of it all, like I told you, that the family did not realize that there was a changeover from one thief to the other. The same thing. The PCs will never realize that the default gateway has changed from R1 to R2. Okay, because the same virtual IP, which has been given configured for R1 and R2, is the same virtual IP that has been given to these PCs here. So these PCs do not realize any change on the default gateway from R1 to R2. And even if R1 comes up, R1 could resume his job of being the active router, and R2 goes back to the standby router and is waiting for another notice from R1. So the virtual router does not exist, just like the dead person. Okay, a person who is dead doesn't exist. Okay, but if that person had belongings like phone number and registration document, those ones can exist, but the person himself doesn't exist. That's exactly what is happening here. R1 uses the IP and MAC address of a device that doesn't exist, just pick randomly. And so what I want us to talk about right now is to look at what are the details, you know, how is it that, and by the way, we can have more than two routers, R1, R2, R3, R4, but only one router is always forwarding at a time. Very interesting concept here. And that is how we have a redundant default gateway, which whereby when one goes down, the other will gonna pick up, and the PCs do not realize any uh, uh, change on connectivity. And so, having said that, the messages exchanged among themselves are just hello messages. And the active router and the standby router, the active router is the one that is always doing the forwarding. In fact, we call it the forwarding router or the active router. Okay. The other one is called the standby because it's always on standby. And the day or the time when the standby router stops seeing hello messages from the forwarding router, and the standby router assumes the role of the forwarding router. And because the new forwarding router now will be assuming both the virtual MAC and IP addresses, the host devices see no disruption in services. And that is a very important concept to provide redundancy even at the level of the default gateway. Now, we have different types of uh, this first hop redundancy protocols. And the first one is called Hsrp, the hot standby router protocol. Hot standby router protocol. This is a Cisco protocol. It's a Cisco proprietary protocol. And that one is for IPv4. Then we have Hsrp for IPv6, doing the same thing for IP. IPv6 network, also from Cisco. Now, we have another one called VRRP. And we have VRRP, which is Virtual Router Redundancy Protocol, VRRP version 2. This is non-proprietary, which means it can be used by any devices. Then we have VRRP version 3, which is actually used by both IPv4, IPv6, IPv4 and IPv6, IPv4 and IPv6. Okay, so that is VRRP, Virtual Router Redundancy Protocol. And then we have the what is called GLBP, Gateway Load Balancing Protocol. This is a funny one. For GLBP, it actually does what is called load balancing, whereby when we are having the forwarding and the standby routers, both of them can actually work at the same time. If the other one stops, the other one is still available, to be transmitting traffic across the network. So from the word load balancing, it can load balance traffic by sharing traffic through both routers. We have GLBP for IPv6, which does the same thing, but for IP version 6 networks. Of course, we have the last one here, ICMP Router Discovery Protocol, which is a legacy protocol, very older one. But the most current ones are the Hsrp, VRRP, and GLBP. Now we're gonna spend a little bit of time talking about Hsrp, the hot standby router protocol. And like I told you, it's a Cisco proprietary protocol in order for a way of providing redundancy at the level of the default gateway, and it ensures high network availability, okay, by the first hop routing redundancy for IP version 4 host and version 6 as well. So Hsrp normally is used in a group of routers to select an active device and a standby device, okay? And the active device is used to forward the packets, and the standby device will always take over from the active device when the active one fails. And so the major function of the standby router is to monitor the operational status of Hsrp group, and they keep on exchanging hello messages. Now, to note down a few details here, routers by default have no been enabled for Hsrp, all right? And they have to go through an election process. That is important to note. They go through an election process to elect the active router and the standby router. They go through an election process to elect which router becomes the active and which one becomes the standby. All right. So normally by default, once you enable Hsrp within the router, by default, the router with the highest numerical IP address, IPv4, for example, is selected to be the active router. And of course, goes without saying that by the second highest IP address router will become the standby. Okay. But like I always tell you, don't always leave the router to make the decisions for you as a network administrator. Okay. You must be in charge of controlling how the network devices you need them to operate. And so you can determine what is called an Hsrp priority, Hsrp priority, to determine which router should become the active router, such that the router given or configured with the highest priority becomes the active, and the one with the second highest priority becomes the standby router. Now, by default, by just enabling Hsrp within routers, all routers will have a default priority of 100, okay? By default, all routers have a priority of 100. But if the priorities are equal, then the router with the highest IP address will still be elected as the active router. Now, to configure the priority, use the command, and we are going to do it. Use the command standby priority. Standby priority, and then you put the number. The priority number can actually range from 0 all the way to 255. The priority number can range from 0 to 255. The default one, as we have said, is 100, but you can change that 100 to any number from 0 to 255. Any number from 0 to 255. Now, it's also important to note that if a router becomes the active router, it will remain the active router even if another router comes online that is having a higher priority. But you can always force a new election process. You can always force a new election process to happen, and you do that using a command. You can actually force, or we use the word to preempt an election. Okay, so to preempt or to force a new election to take place when a router with a higher priority comes online, you need to enable the preemption. And the command, you just say standby preempt. We are going to do all that in a few. Okay, standby preempt. And so with that enabled, a router that comes online with a higher priority will always assume the role of the active router. Now, I want to us to I want us to actually before we do some few configurations here and there, I want us to check on some of the states when a router is enabled for Hsrp. It doesn't just become the active or the standby. No, it goes through some steps or some stages. And the first one is called the initial state. And for the initial state, the router enters, this stage normally entered through a configuration or when the interface becomes available. Then, of course, we have the LAN state. At this step, the router has not determined the virtual IP addresses of the other routers, and they have not seen any hello messages from the other routers. Okay, so the router is actually waiting to hear from the other Hsrp neighbors. Then we go to listening state. At this step now, the router knows the virtual IP of the other router, but it is neither active nor a standby router. It's still listening to hello messages from the other routers. Then we go to the speak state, where the router is now periodically sending hello messages, and this is the point when the election takes place to elect who becomes the active and who becomes the standby. And finally, at the standby state, the router is a candidate to become the next available active router and sends periodic hello messages. It is important to note that both the active and standby routers normally send hello packets to their neighbors after every 3 seconds by default. After every 3 seconds, a hello message is sent among the routers. But if the standby router becomes, if the standby router has to become the new active router, then it's going to wait for hello messages. And if it takes 10 seconds before receiving any hello messages, okay, 10 seconds before receiving any hello messages. And of course, this time can be lowered. You can always lower it so that the transition is much faster. Then if it takes 10 seconds by default, then the router it becomes the new active router. Okay. So to enable the transition to be faster, you don't have to leave it at 10 seconds. You can always set it at a lower time so that the transition is quicker and the transition from one router to the other is much faster. And so at this point in time, I want us to look at a few configurations here and there, and then I'll also take you through some exploration, which you guys can be able to work on later on. So looking at this diagram, we have three routers, R1, R2, and R3. We have PCA on LAN 1 and PC2B on LAN 2. And we have a server, web server actually, connected to the other side of the internet on the service provider network. And so reading the background information here, we're told that spanning tree protocol provides loop-free redundancy between switches within a LAN. However, it does not provide redundant default gateways for end user devices within the network if a gateway router fails. So Fhrp redundancy protocols provides redundant default gateways for end devices with no additional end user configuration necessary. And so by using Fhrp, two or more routers can share the same virtual IP address and MAC address and can act as a single virtual router. And hosts on the network are configured with the shared IP address as their default gateway. And so in this activity, you will configure Cisco hosts hot standby router protocol, Hsrp, which is Hsrp protocol. So you'll configure Hsrp on routers R1 and R3, which serve as the default gateways for the host on LAN 1 and LAN 2. And when you configure Hsrp, you'll create a virtual gateway that uses the same default gateway address for the host in both LANs. And so if one gateway router becomes unavailable, the second router will take over using the same default gateway address that was used by the first router. And so because the host on the LANs are configured with the IP address of the virtual gateway as the default gateway, the host will regain connectivity to remote networks after Hsrp activities activates the remaining router. Okay, so I've read through a very long statement over there. I love more the implementation part, which I want us to do right now. So checking at what is here, we want to see how is it that we can be able to make this to be able to work to our favor. And so let's see how to go about this. So we're going to do a few experiments here just to make sure that we are doing the correct thing. And so the first thing that we are told to do here is that we are going to go to the desktop of the PCA and open the command prompt, and we are going to trace the path to the web server. All right. So I go to the command prompt, and I'm going to trace the path to the web server. The IP of the web server is here. So I'll just say here, I'll do trace that. 209.165.200.226. And so I could expand this so that you could see the path being traced over there. All right. So you can see the path is being traced very clearly there. And we have gone three hops, and the fourth hop is there, and the trace is complete. And we now need to see, something here. I want you guys to be keen enough here. Now, we are tracing the path from PCA all the way to the web server. Okay. And so normally the switches are very transparent, and we might not see much for the switches, but the routers is what we are going to be very keen on. And so we are going to ask ourselves, the first hop here, which is 192.168.1.1, it's which device? And so I could just, zoom this in, and you could see with me that 192.168.1.1 is R1. And so it means traffic moved from PC1, traffic moved from PC1, PCA to R1. It never went through R2 to R1. The second one is 10.1.1.2 right here. And so checking on the table again, 10.1.1.2 is right here, and that is R2. Okay. And we go on and on. The next one is 10.100.100.2. 10.100.100.2. And so 10.100.100.2 should be one of the devices here, and let's just see what that is. 10.100.100.2 is here. It is the inet, which is the internet. All right. So traffic from PC1, from PCA, went through R1 to R2 to inet, and finally the traffic went to the web server, and the IP address of the web server is here. So what have we been able to establish? That PCA traffic went through R1. All right. Let's see. Let's see PCB. Let's see what happens with PCB. We are going to do the same trace over here, and we are going to do it in PCB. We're going to trace the same path from PCB to the web server. And let's trace it. See the trace here. And we can see that the trace is happening already, and boom, it's done. Okay. And we can see the first hop from PCB. The first hop from PCB is 192.168.1.3. From the table, .1.3 is R3. See that here? R3 is .1.3. And you can see it went from PCB. Traffic goes through S3, of course, to R3. From R3, where next traffic go? 10.1.1.2. 10.1.1.2 is actually PCR R2, the router R2. Okay. And then the third one is 10.100.100.2. And 10.100.100.2 is the same inet or internet. And so from internet, the last one is the web server, which therefore means traffic from PC A goes to the same through R1 to R2 to the internet, to the server. Traffic from PCB goes through R3 as the default gateway to R2 as there, and then from R2 it goes to the internet and to the web server. And so we're having every PC taking its own direction. Every PC is taking its own direction, and that is something very interesting to note. And what we want to do right now is that we want to interfere with that smooth flow. We want to interfere with the smooth flow. And so what I'm going to do right now is that I'm going to disconnect the connection between S3, okay, and R3. I'm going to disconnect the connection between S3 and R3. So I'm going to go up here. Up here, we have the delete tool, which is this one here. Okay. So I'm going to click on any white part here, then click on the delete tool. Then I'll click this link just to delete it. Sorry. And it's gone. And I must go back and, click back the select tool. I must go back and click the select tool. Otherwise, if you keep the delete tool like it still is right now, it can delete any other device here. So you must go back and click the select tool so that you have the normal cursor. And then after we do that, I am going to repeat step 2, which means I'm going to try and see if both PCA and PCB can still trace their paths. All right. So let me start with PCA. And on PCA, let me see if the trace will still come. And let's see if the trace is still okay. And you can see everything is still the same. Nothing has changed. All the IPs are all the same, which means the packets are still using the same path to reach the web server. Let me do that with PCB. All right. So I'm gonna expand PCB here. And on PCB, I'll bring up the previous trace again. And let's see that here. Okay. Okay. You have seen a symptom here. Request timed out. That's a very serious concern. If you ever see that, because traceout is always a bit faster, if it starts with the request timeout, then there is a problem sometimes, especially if you get another second one, request timed out, and it keeps on coming. You need to be worried at this point in time. So we have the third request timed out. The request is being timed out. All right. And even before that is complete, we can already see, yeah, you can see that as we wait for it to complete and it still requires timed out, you realize that we have cut off the default gateway of PCB from connecting to that network. And so PCB only knows about R3 as the default gateway. It doesn't know about R1. The only person who knows about R1 is PCA, okay? And so this was the only alternative that PCB has. And this rings in our mind something that, Having learned about Hsrp, we need to install or to configure Hsrp in this network so that we don't have a section of the network giving us request timed out. And when you see request timed out, it means the PCs on that network, they will no longer be accessing the internet. The browsers will keep on giving, errors or keep on loading and loading without having that access to the internet. This is not a very good sign, friends, and this is something we need to work out on. Okay, it will keep on going until it gets finished by itself. So I could break this sequence by just pressing Control C, because it will go on and on. And I will now put back that cable, and I will take a cable down here and pick a copper straight through and connect G02 here, gigabit Ethernet 02, and put it on G00 of this router. I might want to just fast forward it so that it could be green at the same time. And so by going back to PCB and doing the same thing, we should now be able to, once it has been restored back, we should see our traces as usual. You see that? That is a normal condition. Now we don't want to rely on that normal condition, and that's why we are learning something very new. So at this point in time, we now want to activate Hsrp on R1 and R3, so that R1 will be our active router and R3 will be our standby router. So we are going to work on the interfaces of the two routers facing the switches. So for R1, we'll work on interface G0/1. This network seems to already be loading. You can see some routing protocols. If I say show IP route, show IP route. Oh, let me do show IP route OSPF. And just saying show IP route OSPF, you realize that we're having some OSPF network here. You can see it's represented by an O, but we'll talk more about it soon enough. And it's doing some load balancing here. Anyway, that will come later on. So the thing is, we want to get into that interface. So let me go to the global configuration terminal, and I get to interface G01, which is the interface facing the switches. So I just need to say int G0/1, and I need to specify the second version of Hsrp, and I'll just say standby. The command for configuring Hsrp, you will never use a command starting with Hsrp. So the word that you need to mostly note is the command standby. It says standby version 2 is the secure version, correct? Having said that, then we need to do the next thing, which is now configuring the IP address. And this is the virtual IP address. Okay, this is the virtual IP address which is going to be shared by the two routers. So you say standby 1 is the group number, I mean, the group number is just used to identify the virtual interface between routers in a Hsrp group. And so we are going to use group number 1. So standby 1 IP is 192.168.1.254. 1 and 2, 168.1.254. Okay. Standby 1 IP 192.168.1.254. This is configured on the interface. The version is also configured on the interface. So this is the virtual IP address. Good. So we press enter. And the moment I press enter, you realize that the states are already moving here. We are ready from init. Okay. And after some time, of course, it will keep on moving. I might want to say to show standby. You can see it has moved from init to speak to standby and then to active. So this router is currently the active router. So let's say if you standby, a couple of things to note here is that our router is in the active state, number 1. 2, the virtual IP address is already here as we have just configured. Of course, you can see the virtual MAC address. Okay. You can see the hello time here is 3 seconds and the hold time is currently 10 seconds. This is the time that when the standby router attacks without seeing hello from the active one, then it becomes the active router. Currently, we have not enabled any preemption, so it is disabled. And the active router is the local one we are working on currently. It's the local one, but we do not know who the standby router is. It's unknown. Okay. The priority currently is 100, the default one, and the group is group 1. Now, the next thing we need to do is we need to change, since R1, we want it to become the active router, we are going to give it a higher priority than 100. So we say standby 1 priority, and we give it a priority of 150. Standby 1 priority is 150. And so if we can be able to say do show standby again, you can say that the priority has now changed to 150 and it is a configured one. Okay, it's a configured one. Then the last thing we need to do is that we want this R1 to be the active router, and if the standby router, if this active router loses connectivity or becomes it is connected from the internet or from the network, and R3 becomes a new active router, we want it, when it comes back, we want it to resume the state of being the active router. Want it to resume the state of the active router. And so we must enable preempt so that it can always force itself to become the active router when it comes back. And this normally happens when you prefer a specific router to be the active router. So what we do, we say standby 1 preempt. All right, standby 1 preempt, and we do that, and now we are good to go. We are good to go, and the only thing we need to do is now we need to of course we can show that standby preempt is now there. You can see preemption is now enabled here. So we now go to R3 and you do a couple of just a few things. not so much. Okay. So we say we get to the interface G01, should be the one. Let me just see here. Okay. I could go to the table and just check on that. And check on router R3. And the network on 192.168 is G00. All right. Very important to note that. So interface G0/0. Then the instruction was very clear that for R3, we are only going to configure standby version 2, version 2, and 1C is the virtual IP. You see, standby 1 IP, the IP is 192.168.1.254. Okay, and look at that. This router is transitioning from the init state, and we can see it's moving. It hasn't finished yet, and it has moved from init to speak, and it has gone to standby. Very important. From here, we can actually say show standby, and you can see a few things here. One, this router is currently on standby mode. Okay, and I want to bring up the other router to compare both of them. R1 is here. Look at these comparisons here. All right. So this router is currently, R1 is currently active, and R3 is standby. R1, the virtual IP address is here, 192.168.1.254, and the same virtual IP address is 192.168.1.254, being shared by the two routers. The virtual MAC address should be the same, as you can see it here. This is the virtual MAC, and this is the virtual MAC as well. Preemption is disabled on router 3. Preemption is enabled on router 1. The active router is a local. Active router is given on another IP address. But here, standby router is the local. Look at priority. Okay, it's saying standby router is unknown. We need to bring up the new one so that we now know standby router is on this IP. Okay. So the active router gives us the exact or the real IP address of the standby router, and the standby router gives us the real IP address of the active router. Okay, but they share the same virtual IP. The priority is 150 for the standby router. The active router is left at a default priority of 100. All of them are in group 1. Group 1 here. One is on interface G00, one interface G01. All right, having seen that comparison, we now need to see something more here. Now, we need to do one more thing. And what you need to do is that we need to change the IP address of the PCs to the virtual IP address. And so we go here and we say 192.168.1.254. All right. We go to this PCB. We go to the IP configuration and we give it the virtual IP address as the default gateway. Excuse me. All right. So having seen this, we now want to test our network. Okay. And this is where I'm going to need you guys to be a little bit keen. All right. And so what we are going to do is that we are going to test and see how the packets are moving. We know that currently, theoretically, R1 is the active and R3 is the standby. So how does it work? So let's go to the PCA, go to the command prompt. And what we are going to do is that we are going to trace the path again. So we start from PCA. And this is the path we are tracing. And looking at the traced path here, we realize that the first path is through 192.168.1.1. And that IP, checking at our table, is the IP address of R1, 192.168.1.1. It is the IP address of R1, which is currently the active router. Then 10.1.1.2. 10.1.1.2 is the IP address of R2. 10.1.1.2, IP address of router R2. All right, which means therefore that traffic from PCA goes through R1 to R2. The third one is obvious, 10.100.100.2. 10.100.100.2, as we had seen, is the IP address of the INET, the internet. All right. And that is actually the internet cloud, which we see here, 10.100.100.2. The last IP is the destination IP address, which is the web server. And you can see the web server's IP address is right here, 192.165.200.226. All right. So far, PCA has passed the test because PCA is using the IP address of the active router, as we had seen here. The active router is here, is R. Let's see what PCB is using. So we open PCB, go to the command prompt, and we want to trace the path again. And I hope you can see the previous result of this PC. Traffic was for PCB, traffic was going from PCB directly to PCR3 or to R3, then to 10.1.1.2, which we have seen is for R2, and 10.100.100.2 is for the internet, and the 209.165.200.226 is for the web server. Now let's see if there's any difference. So I'm gonna bring up the trace up again, press enter, and look at the difference here, if you can see it. Now PCB is no longer using R3 because of a simple reason. R3 is currently the router on standby. It is not the active. The packets are no longer going through R3 for all these two networks. Traffic from PCB is also going from PCB, of course, through S3 and S1, and it comes through R1. Then from R1, it goes through 10.112, which is R2. Then 10.100.100.2, which is the internet. And then 219.165.200.226, which is the internet. So traffic from PCB is also going via R1 to the internet. And so currently, the only default gateway that these two LANs here, LAN 1 and LAN 2 know, is R1. Is R1. Now, the question is one. What if we disconnect the link between R1 and S1? That's what we are going to do next. So like I did, I go and I pick the delete tool, and I come and I want to delete the link between S1 and R1. All right. I go and click the select tool, and quickly we could see a few things here. We could just check here and check what is the current state of this router, R1. R1, the state is no longer standby or active. It's actually the interface is down. So it is at the first stage, which is the init. The virtual IP is still here and the virtual MAC. Then the active router is unknown. Look at this. Active router is unknown and the standby router is unknown. Of course, the priority is 150. Okay. This router is in darkness. It's been disconnected from the network in some way. So let's look at the status of R3. So for the status of R3, when we check show standby, look at currently R3, which has been the standby router from up here. The state was standby. R3 has just transitioned and is now the active router. All right. Virtual IPs here, virtual MAC. Active router is this router, and this router R3, it does not know who the standby router is. It's unknown to it. Of course, the priority is 100. So let's put that into action, and let's see now that R3 has become our new active router, is it going to transfer the packets or not? So we start from PCA right here, and looking at the results we have seen from PCA 1.1. Let's trace the path again. Look at that. Let's just wait patiently in a few seconds and look at it. Very beautiful. Now the first hop is no longer R1 at 1.1. The first hop is now R3 at 1.3, then to R2, then to the internet, then to the web server. So traffic from this RPCA is now moving from PCA to S1 to S3. Then it's now going to the internet through R3, and it goes to R2 to the internet to the web server. That is RPCA. What about PCB? Is it gonna do the same thing or it's gonna be different? You can see it was going through R1. So let's trace the path again. Look at this. Look at this, guys. PCB is no longer going through R1 as its active router default gateway. PCB is now using R3 because R3 is currently the default gateway. So remember this. The two PCs on different networks, we configure them the same default gateway, but they keep on shifting, and the default gateway configured them was 1.254, which was the virtual IP address. So these PCs, their IP addresses remain the same, but if you trace the path, they keep on having connection, even though the physical default gateway connected is down, but we configured a technology called Hsrp, the hot standby router protocol. It enables these PCs to see no interruption in connectivity. and they continue to connect to the internet, even though the physically connected default gateway is down, but the routers have been configured to work as a team, as virtual router. And you can see that we just lost a connectivity from S1 to R1, which was previously the active router, but the PCs are continuously accessing the internet through another router R3, because these two routers are continuously communicating within every 3 seconds to be able to exchange hello messages. And so this is how, you know, you guys realize that we have bigger networks which don't need such interruptions. Think of Safaricom, for example, in Kenya, which is one of the major telecommunications companies. People rely on it for mobile money transfer, for making voice calls, for sending text messages, for internet connectivity. And so they can't want to fail even for a few seconds. That is not what they do. They want their customers to continue providing internet. And apart from this, they can be having different service providers providing them with internet at a higher tier level. Now, what happens if I restore this link, and because I had configured R1 with what is called preempt to be able to force itself to become the new active router, even though it had lost that position. So let me pick an Ethernet cable, copper straight through, plug it on R1 here, and put it back to S1. And we are going to look at this one. I could fasten it by clicking fast forward here. And you can see it has moved all the way from init to speak, standby, and to active. And even the OSPF process, which had gone down, is now loaded to full adjacency. And we learn about OSPF at the beginning. We learn about it was the end of this course and the beginning of the next one. So you realize that this has gained connectivity, and by just checking on if this router what is the status, you can see here it's back to active. It's back to active, and now the standby router is known. Okay, you could compare that with previously when the interface was down and the standby router was unknown and the active router was unknown. We could go back to R3 and check at R3 and look at who is this guy now. This router is currently back to standby. A few seconds ago, it was the active router. You can see, all right? And a few seconds ago, it did not know who the standby router is because it was the active. Right now, it knows who the active router is because it is the one on standby. And we could trace the path, just one more trace here. We could see the last trace, they were using R3. Now, the next trace, let's see what they're going to be using. There we go. There we go. There we go. And now they are using, expand this. Yeah, you can see they are now using R1 here. From R3, now back to R1 because R1 is currently the active, and the rest is R2, internet, and the server. The same thing with PCB right here. You can see the last trace was there at R3. Let's see what the trace is gonna be here. Look at this. This was R3. Now the next trace is R1. And so the routers, the PCs do not experience any change in performance. Now my question is this, guys, ladies and gentlemen, how will this look like in a bigger network? And I have a simulation of a very big network here, if you may. This, it looks like a joke, but it's a big network. If I just click here, you see that this is a network in Seattle in the US, and they have a data center too here. And I could click back here. I'm going to click on that data center and you'll see what is there. I have another in Toronto in Canada. I think all these are in North America. This is Toronto, and Toronto has data center 1. All right. And we have the headquarters here in Winnipeg, and they have a branch office right here. So let's get into each office. Let's start with Toronto. And let's look at the data center 1 in Toronto. And I'm going to click on this data center 1. It's a huge one, a huge network. Look at this. How many? We have, these are server. This is a data center having several servers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 here. So we have 1, 2, 3, 4, 5, 6. So 6 times 4 is actually 24. 24 plus 4 more servers here are 28. So we have 28 servers. Every 6 servers has here 2 layer 2 switches with a patch panel up here, 2 layer 2 switches, 6 servers with a patch panel up there, 2 layer 2 switches, and they are not imaginary switches. I can actually click on the switch and it's gonna open right here. And these switches have so many things. I could just get into each of them and just say, I could say show VLAN brief. I don't know how many VLANs they have. And we could see that we have a couple of VLANs here. Yes, we did see VLAN 99, of course, using the default VLANs. We could check, I could just say, let me just view another setting here. If I say here, show spanning tree, and you can see a couple of things here we did talk about last week. The port channel actually configured here, port channel 1. If I say show, we could view the ether channel summary. So show ether channel summary, and you could see we have port channel 1 here, and it's using LSEP, the link aggregation control protocol, and the first Ethernet 1 and the first Ethernet 2 are the members of the ether channel. So that is just one switch, and of course we have these aggregated switches here carrying traffic from all the other switches. And you could also just look at what is here. Show ether channel summary, port channel 1 using LSEP. Show VLAN brief, and it did have this just VLAN 99 there, and show run. And viewing show run, oh, there's a couple of port channel is there. There's trunking, I can see is there, and there's it's a couple of things put here. This is within the switches. I am just logged into one of the switches within this data center. And let me get to the routers, for example, and pick on one of the routers. There are 2 routers here. I believe these routers are being configured with and you can see that. You can see that obviously it's here. I could say show standby. Show standby. Look at this. This router is currently an active router. Okay. And there are two groups here. There's group one. This router is group one. It is standby for group one. And the virtual IP is here as usual. The preemption is enabled, of course. Active router is on that IP. Priority is 50. Look at that. This is group two. Now for group two, that's group one. For group two, this router is active. So a router can be active for another group and standby for another group. And the virtual IP is right here. Obviously, preemption is enabled here, and the standby router is found there, and priority is actually 50 here. And no, priority is 100 right here, the default one, and that is that router. If I can check on the other router, the first one, and I could also see here, and we'll say show standby. This router also has two groups. Group one, it is the active router, whereas the other router, group one, it was the passive router. The virtual IP and the MAC are also there, of course. The active router is the local one, and the standby router's IP is there. The priority is at 100 right there. And for group two, this router is the standby, and the virtual IP right there. And it's funny that this second one has a priority of 50 as well. All right. So that's, I mean, this is something I'm going to need you to explore. And I'll tell you why you need to explore it. And of course, there are connections from this switch here going to the router. I could say show run. And show run gives me the trunking being done on port channel 1, port channel 2, port channel 3. Look at this, port channel 4. So this will be a very good one. I'm interested to see show span. I'm interested to seeing that. There's a lot of stuff here that you might want to learn. We have 5 port channels here. And this is increasing the speed, because the speed between, if you look at the switch up here, this switch is connecting the routers up there and connecting the switches down here. So that's why has to increase speed between its links to push traffic from all the servers available here. And no wonder this switch has several port channels. And from the look of things, this switch has all the designated ports, which means this switch must be the root bridge for this network. You can see the bridge is the root there. And I'm more interested to see, if I say show ether channel summary, and you can see all the 5 port channels are all here, and all of them are using the LSCP as a protocol, the link aggregation control protocol, and 13, 14, 15, and 16, so on and so forth. Okay, and so it is interesting, just exploring here and looking at how things happen here. Now let's go to another server room or another data center. And let's look at a data center in Seattle here. And in Seattle, we have data center 2, and I'm going to open it. And data center 2 also has 28 servers. 2 times 4, 8 plus 4 is 12 switches. 28 servers, 28 switches. I mean 12 switches and then 2 routers. And I will be interested, obviously, to look at this switch here because it's at an aggregation point. And I would say show uh, show spanning tree and realize it has several port channels here as well. Okay, and it does add port channel 1, 2, 3, 4, and 5 there. And if I say show ether channel summary, and you can see the 5 port channels available here, and these are very important as a point of interest for our learning here. And so the servers are also clickable, by the way, and you could check at some of the services that are running on this server. HTTP is currently put off. DHCP seems to be off as well. DHCP version 6 seems to be off. Or TFTP seems to be on. So you can see a couple of IIS images for different operating systems actually kept on a trivial file transfer server. DNS is off, syslog is off, AAA seems to be off. The network time protocol is actually off as well. Email services are off, FTP are off, and IoT are off as well. Virtual and VM management and the radius authentication protocol are also off. So again, different servers playing different roles. So you can always explore and find out. Of interest, of course, is within our routers, and we want to check. We want to check the current state of Hsrp here. So we say show standby, and clearly you can see that for group 1, it's the active router and the virtual IPs are here. And the standby router is found on this IP on 0.2. Then we have group 2 here, each is in a standby state, and it has virtual IP addresses right here and the MAC addresses as well. And the priority is 50, as you can see, and the active router's IP is there as well. Having seen that, let's look at the central point, the point of aggregation, which is at Winnipeg. And I'm going to look at the aggregation point, which only has one wiring closet, which is connecting the two service providers. So I'm going to get to this router, and most probably this router might only have the routing table, show IP route, right? And obviously there are some static routes here. You can see them with the letter SS there, and the static route. The last 3 chapters of this course is for static routes. Show show standby. I don't think this element of standby, there's none here, because these ones are aggregation points for our networks. I don't know that there are any extra VLANs here. Show VLAN brief, and not so much VLANs to talk about, but show run will actually give us more information. The host name is ALS1, and the interfaces are all here. I didn't see any trunking down here. Not so much again. Yeah, so of course the PCs are here, and we might want to check on the desktop here. Of course, checking on the IP configurations. We could say IP config You could see there's a couple of IP configurations here. Mostly they are version 4 of IPs right here. And, of course, the other one as well. So now, before we just bring this to a close, there's something in store here for you guys for this particular activity. You have been seeing me explore here, and what you're needed to do is that they need you to make some adjustments on this big network. This is a very large network, and so you are going to expand the current data center, and you're going to determine what equipment is required to add one new rack of equipment to both data center 1 and data center 2. So there are very clear instructions here to follow. And so use these instructions to modify this data center. So click on it, and you are going to make sure that it integrates with the rest of the network. And, I think you will be adding it. There, of course, the Ethernet cables are already here. Those are copper straight through cables. The laptop is on the table here, and the console cables are here. And you are actually going to add devices on this particular device. I think for here, you might be going to put one server here, I suppose so, and connect it to the network. For data center 1, let me see what you people are going to do. I think this is where you're going to add a whole closet, with switches, and you are going to definitely do that here. Let me just close this here. Look at this. This is the space that you're going to add servers in and some switches over here. And you can see there are more cables here, and console cables, of course, and you're going to integrate them. So use the instructions given here to do a good job. And when you finish and this network is working, you've configured the IP addressing, and you have been able to troubleshoot, and the whole network is working as it's supposed to. You pat your back and you say, I made it. So this I'm going to give you 2 activities for your assignments. So the first activity, obviously you note that down, is on 933. 933 is the first activity. It actually looks like this. First activity. Then the last activity, I suppose, is this for the data centers, is on 934. Sorry, is it 934? Yeah, 934. So 934 is the other assignment that you guys are going to be working on. Otherwise, I don't know whether there are questions from the class. That marks the end of this class. It's been quite a journey here, studying about the Hsrp, and you have seen how well it is implemented even on a bigger network. Needs 2 routers to be able to provide redundancy. Imagine a big network like this. If they only have one default gateway, the whole clients will go down if that default gateway goes down. So they must have another router which is playing the role of a standby router. They are on standby, so that wherever the active one goes down, then the standby picks up, and the network interruption doesn't occur at any one point. Otherwise, that's actually the end of this class for today. I don't know if there's